We'll wait for others to join. So welcome everyone to week 10 tutorial of the course Fluid Mechanics. So we are approaching towards the end of the course almost. So I hope everyone has been regular to the lecture videos by the professor on the NPTEL portal and regular to your assignments as well as the exam is approaching. The revisions are also going good. I expect that. As well as those who have missed, they might have watched the tutorials, live tutorial sessions, which are already put on the my YouTube channel. The name of the channel is NPTEL with Varnit. I hope everyone has been regular to that. So in the last tutorial, we ended up with the concept of circulation and then vorticity definitions. Last topic was that. And today we'll start with velocity potential functions and the stream functions. So let me share my screen so that we can start. I hope my screen is visible. Great. Check. Okay. So what is velocity potential function and a stream function basically? Okay. So these are nothing but some mathematical function to define the rotationality of the fluid. Okay. So under specific condition, these functions are valid. So velocity potential function, again, both are, or the stream function side, both are function of space and time. Okay. Velocity potential function is a smooth point continuous scalar function. It is a function of space as well as time. And it is defined for irrotational flow. Whenever the flow is irrotational, then only we define the velocity potential function. Okay. So when we say that irrotational flow is there, that means it's a potential flow, because that for that only the velocity potential is defined. And it is defined in such a way that when you do the partial derivative of that potential function, that gives the velocity in the particular direction. Okay. All right. So let me write all these points. So we'll make a tabular format for writing the points for velocity, potential, and string function. Okay. So first is velocity, potential, and it is denoted by symbol phi, whereas stream function that is denoted by symbol psi. Okay. So these are your two functions. So first point for velocity potential function is that it is a smooth continuous point function I hope everyone knows what is point function, what is path function or state functions. All these difference have been done, and you might have studied in thermodynamics. So those who are independent of the path, point or state functions, point functions, point scalar function. I should write point and a scalar function. Another point. It is a function of space and time. It is a function of space and time. That is, your phi is nothing but function of x, y, z as well as time. Okay, x, y, z and time. It is defined for irrotational flow. Very important point. It is defined for irrotational flow. Okay. So irrotational flow is also known as potential flow. Flow is also known as potential flow. Okay, is also known as potential flow, and it is defined in such a way. I'll extend this difference line. It is defined in such a way that partial derivative of phi in particular direction gives velocity component in that direction. Okay, so that means when you do a partial derivative of, I think I should again extend this. It's a quite big comparison table. So when you do, that is, your u is nothing but partial derivative of phi with respect to x. V is nothing but partial derivative of phi with respect to y in that direction. And w is nothing but negative or partial derivative of phi with respect to c. Okay, so all the proofs are available in the textbook. We won't go to the proof. Okay, or either you can also write with a positive sign depending on what is the direction of the flow when you are defining your potential function. Okay, or you can say u is nothing but dou phi by dou x. So it depends on the sign convention that textbooks considers. Okay, sometimes they consider clockwise to be positive. Sometimes some books consider anti-clockwise to be positive. Okay, so it depends on that aspect. And whenever we say that, whenever there is irrotation, that means potential function will be defined. Okay, potential function will be defined. So whenever there is irrotational flow, then the potential function will be defined. Okay, but vice versa is not true. Always remember that. Vice versa is not true. So I'll write that point as well. Let me extend this line more. Whenever irrotational flow is there, then phi will be defined, but vice versa. But if we say that phi, if I'm saying that the flow is in rotation, then definitely phi will be there. But if I say that phi is defined, then can we say that flow is irrotational? Yes. Okay. So if I say that flow is rotational, will phi will be there? No. Okay. Will be defined. All. Next. So every velocity profile satisfy its continuity equation. Already we have studied in the last tutorial. So when I say for an incompressible steady flow, what do you mean by incompressible? That means your divergence of velocity is equal to 0. We have seen this condition. Why? Either the flow is compressible, uh, steady or unsteady, but if the flow is incompressible, then divergence of velocity is always 0. Okay. So if I say for incompressible steady flow, our divergence of velocity is nothing but 0. Okay. That means in terms of Cartesian coordinates, du by dx plus dv by dy plus dw by dz is nothing but 0. Okay. What is u? We have just wrote u is dou phi by dou x, v is dou phi by dou y, w is dou phi by dou z. Okay. So I put here dou by dou x, dou phi by dou x plus dou by dou y, dou phi by dou y plus dou by dou z. Instead of w, you put dou phi by dou z. Is nothing but equal to 0. Is nothing but equal to 0. Okay. So what can we write? It is nothing but, let me extend this more. You can say that it is dou square phi by dou x square plus dou square phi by dou y square plus dou square phi by dou z square is equal to 0. And that is nothing but your one of the formation of a Laplace equation. So if for a Laplace equation, so that is del square phi is equal to 0. Okay, del square phi is equal to 0. So if my function has f of x Laplace is equal to 0, you can divide it in two ways. One was defined by Laplace, other was defined by Poisson. So from the concept of Laplace, that is Laplace equation, states that del square f is equal to 0, or Rf here is nothing but phi. Okay. del square phi is equal to 0. Okay, so that means it is a 0. Whereas from the Poisson's equation, it says that del square phi is non-zero. Non-zero. Okay, so here phi will not exist. If, as per the Poisson's equation, phi doesn't exist, that means my flow is there, rotationality is there. But when I say my Laplace equation, my del square phi is 0, that means my flow is irrotational, and that means it satisfies the Laplace equation. All right. So we can say that phi is defined only for irrotational flow. Phi is defined only for, so both have just stream function or potential function, nothing but the mathematical expression to understand the rotationality of the flow. Okay, it's defined only for irrotational flow. It's defined for only for irrotational flow. Okay, so I think I have written this point. It is defined in such a derivative. It is defined. Okay, I'll not write this point. Sorry, my bad. I should write that. This. If phi satisfies its Laplace equation, then phi is valid. If phi satisfies its Laplace equation, then phi is valid. Okay, then only we can say that phi is valid. And if not, then phi is wrong, because our continuity equation is always right. Always remember that continuity equation is always right. And in that case, we need to find the phi, new phi with respect to the from the continuity equation. Okay, and phi is defined for 3D flow. It is defined for phi is defined for three-dimensional flow. That means for flow, three-dimensional or two-dimensional flow, it can be defined. Now let's come to the stream function. Let's come to the stream function. So what is a stream function? Again, it is a mathematical expression. So it is a scalar point function, but not continuous system. So there is a difference. That was also point and scalar, but that was potential function was continuous and smooth as well. But it is a scalar and point function. Both are function of space and time. Okay, and again, it is defined for continuity equation, that is for conservation of mass, and it is defined in such a way that derivative of the stream function in a particular direction give the velocity component in the perpendicular direction. Okay, always remember that. And stream function is only and only defined for two-dimensional flow. Only and only defined for two-dimensional flow. Okay, not for three-dimensional flow. Okay. That's right. It is a scalar point function. It is defined. It is a function of space and time. That is psi is function of x, y, z, t. Okay. It is defined for continuity equation. It is defined for continuity equation. Okay. It is defined in such a way that derivative of stream function the derivative of stream function psi in a particular direction gives velocity component in perpendicular direction. Perpendicular direction. Okay, perpendicular symbol is this, and it is defined only for two-dimensional incompressible flow. It is defined only for two-dimensional incompressible flow. Okay, always remember. So we can say that velocity, when we are doing and we are assuming anti-clockwise or counterclockwise, we assume it has a positive direction and clockwise is negative. So velocity u can be written as minus dou psi by dou y. If you do a gradient in y direction, then it will give velocity in the perpendicular direction to that direction. So perpendicular to y is x, and velocity v will be d psi by dou x. Okay. So when I'm going from y to x direction, when I'm doing the derivative in y direction, so I'm taking the velocity u. So I'm going clockwise direction. So I'm going. So suppose this is y, this is x. So when I'm doing the derivative over this y, and this u isn't defined in x direction, so I'm doing basically clockwise. You can learn like this through and along. That is why clockwise have a negative sign. Okay, and similarly when you are going from v is here and derivative is doing here, so you're going from here to there. So that is why it is anti-clockwise. We assume that this positive, or vice versa, as per the textbook convention. Okay, or you can also say that u is nothing but dou psi by dou y, and v is nothing but minus dou psi by dou x. Okay, any of that you can take. And you know that how the rotationality is defined. So it can be defined for both rotational and irrotational. I have not nowhere said that stream function is not defined for rotational. Stream function can be defined for both rotational and irrotational, whereas potential function is only defined for irrotational flows. So as per rotationality concept, which we did in the last tutorial, from rotationality, we know that what is the value of omega. So only u and v are defined because it is defined for two-dimensional flows. So half of dou v by dou x minus dou u by dou y. Okay. So what is v? Dou y, dou psi by dou x by dou x. And what is u? U is nothing but dou psi, negative of dou psi by dou y by dou y. Okay. So if you do, it is something looking like dou square psi by dou x square, dou square psi by dou y square. Okay. So it again shows omega is nothing but half of grad square of psi. Now we have to see it is 0 or non-zero. So again, we have said that it is defined for which condition? Incompressibility, it should satisfy. So when I'm saying that my dou square psi is 0, if my dou square psi is 0, that means we are saying about Laplace equation. Laplace equation says that dou square of function that is psi is 0. So that means my omega of c is 0 in the z direction is 0. Okay. So that means there is flow is irrotational. But if I say, as per Poisson's, rho square of psi is non-zero, that means omega of z is non-zero. So that means the flow is rotational. So my psi function can be defined for both rotational and irrotational flow. So there will be a situation of flow net. So when I'm saying that, only rotationality is there and psi is stream function. So that means it denotes streamlines. Okay. So I say these are my streamlines, and each streamline has a psi value, psi1, psi2, psi3. I'll prove that why psi1 is constant for a particular streamline, why psi is, and for different streamlines, stream function values are different. Okay, but there is no rotationality, or there is no irrotationality. It is rotational. So if flow is rotational, you can't define potential function. But if my flow is irrotational, so again, first of all, I'll draw the stream functions, psi1, psi2, psi3. But this time I'll draw potential functions as well. Phi1, phi2, phi3. And this gives us nothing but a flow net. And both of these are perpendicular. Okay, all of these are. So this is nothing but your flow net. Okay, where del square of psi is 0. Del square of psi is 0. So if psi satisfies its Laplace equation, then flow is irrotational. Otherwise not. So if psi is defined for both rotational and irrotational flow. Okay. So here del square psi is not 0 on the right hand side. On left hand side, the del square psi is 0. Okay. So I'll write the point. If psi satisfies its Laplace equation, then flow is irrotational. Okay. So otherwise it is rotation. So psi is defined both for rotational and irrotational flows. Okay, it is defined both for rotational and irrotational flows. So why? So from looking to this diagram of flow net, why we say that we defined a potential function? Why only just with a stream function we cannot go ahead? Or so one thing is that stream function is defined for only 2 dimensions. When we want to go to the 3 dimension, we want a potential function. You cannot visualize the fluid and say that yeah, it is rotational, it is irrotational by just visualizing through the naked. We need some mathematical expressions. These are your mathematical expressions. So to differentiate through the flow net, we need, if we say only if my flow, streamlines are present, we say that it is a a rotational flow. But if stream lines as well as my potential lines are also present, then we say that it is a irrotational flow. Okay. So this is nothing but your mathematical concept to define. Okay. So this is a pure table for comparison of stream function and velocity function. Okay. Now, what is the physical significance of this stream function? Let us understand from the physical aspect. Physical significance of psi. Suppose I have a axis like this of x and y. This is y-axis. This is x-axis. My streamline is defined in such a way like this. Okay, this is my streamline. Okay, and there are fluid particles eventually. where the flow is happening. Okay. So if I say when I'm moving from point 1 to point 2 here, that is psi 1, suppose this is psi 1, to a point 2 psi 2. I initially don't know that psi is constant. Okay, I told you now I'll do the proof and explain the physical significance of it. So I say that psi is nothing but your function of x and y as well as time, but let us assume it is only a function of x and y. Okay, only a function of x and y. So when I was saying here psi is function of x, y, z, and t. So either you take x, y, either you take y, z, or either you take x, z. Not all three together, because it is only defined for two-dimensional fields. Right? So psi is a function of x and y. So let us do a partial derivative of psi. So that means dou psi by dou x dx or dou psi by dou y dy. Okay. So what is dou psi by dou x? That is nothing but your velocity v dx plus dou psi by dou y is nothing but your velocity u, negative of u dy. Okay. So it is nothing but v dx minus u dy. This is your stream function. Okay. So we know that what is streamline equation? From streamline equation, we understood in past tutorial, what is streamline equation? It is nothing but dx by u or dou x by u dou y by v. So can you write v, just cross multiply and do the transpose, u dy is nothing but 0. Put this value here, v dx minus u dy is 0. So dou psi is 0. So therefore, dou psi is 0 for a streamline. So that means for a streamline, change in the stream function is 0. If change in the stream function is 0, that means psi 1 minus psi 2, 0. So both are equal. Psi 1 is equal to psi 2. Psi 1 is equal to psi 2. Or I can say that if I do integration of dou psi and integration of 0, so that means your function psi is nothing but constant. So for a particular streamline, my function psi is constant. Streamline is the line joined by the same stream functions. Okay, for one particular streamline have same stream function. So I say that my dou psi is 0. But if suppose you want to consider a point like this, okay, psi 3. So psi 3, there is no psi 3 is at a point on another streamline. So across the streamline, suppose this value is 0, suppose let us say psi 3 is 0. There is no streamline. So you can say that the difference dou psi is non-zero here. You will observe that because psi 1 is non-zero and psi 3 is 0. So dou psi will be non-zero for this. Okay. Streamline is not constant across, potential function is not constant across the streamline, but along the streamline it is constant. Okay. So that means streamline is the line joined by same stream functions. So psi is constant along a streamline, but not across. But not across the streamline. Okay, but not across the stream. So that means I can say that if I have set of streamlines, so this is psi 1, this is psi 2, psi3. For a particular streamline, psi is constant, but that for a different streamline, psi is not constant. So that means here, every point is psi1. This point is psi1, this point is psi1. So I wrote psi2, psi1. Okay. Similarly here, this point is psi2, psi2, psi2. And this point is psi3, psi3, and psi3. And the difference along this is d psi is always zero for every string. Okay, for every string. And along the streamline, there is no discharge happening because flow is along the streamline. If you go from here to here, if you're going from here to here, we observe that is there any discharge happening? Anything is discharging, only the flow is happening. There is no discharge. So along the streamline, the change in the discharge is zero. This discharge is happening, but change in the discharge is zero. Okay. So if I say my streamline is like this, so this is also psi, this is also psi. Okay. And along streamline, along change in my discharge Q is zero. Along it is zero. So discharge per unit depth, since my psi is defined only for 2D flow. This is nothing but your discharge per unit depth, because z direction is zero. Depth is in the z direction. Okay. So that means dou psi, mod of dou psi is nothing but or dou q or dq. Okay. So discharge per unit depth is nothing but, if you want to calculate the discharge value, it will be across the stream. It will be across the streamline. So suppose I get a set of streamlines. Okay, like this, psi1, psi2, psi3. Okay, so across the streamline, there will be a discharge. Okay, so Q is nothing but discharge per unit depth, Q1, or Q you can say, is nothing but psi1 minus psi2. Okay, so along the streamline, stream function is constant, psi is constant. Streamline is nothing but a locus of constant stream functions. So we can write that streamline is locus of constant stream functions. Okay, and streamline is defined by this charge is psi1 minus psi2. So we can also prove this thing, psi1 minus psi2 thing. Let us do. So suppose an x is like this, y, x. So suppose I have two streamlines, psi1, psi2. Okay, I suppose that this is something kind of arbitrary shape. Let us take. Okay, so this is point A, this is point B. Okay, this is point A, point B. So let us draw some projections of it. So this is dy direction and this is dx direction. Okay, so this discharge which is happening here, Q, will be bifurcated in two different directions, dq, across the streamline, that is across the streamline which is happening, will be bifurcated in two parts. Okay, dq will be bifurcated in two parts. That is first in the y direction, dq1, and here in x direction and the y direction, dq2. So here depth is always unit depth, always remember. So if I'm doing this area, so it will something look like this, where discharge is happening, that is dq1. Okay, and this is your dy, and this is nothing but your 1. Okay, whereas let us change the color for this. It is looking something like this. This is dx and this is 1, and here this charge is happening dq2. So we can say that from the steady state equation, steady state, whatever mass enters, rate of mass enter is equal to rate of mass exiting. So the total dq is nothing but dq1 plus dq2. Okay, and what is dq1? That is nothing but velocity into rho av. Density is rho into area into velocity. Area dq for the dq1 is nothing but dy into 1 into velocity is in the x direction. That is how much? V. Okay, v dy x into 1. Sorry, if I'm taking this is my dq. So dq1 is nothing but this one. So area is dy into 1 into u, and in the x direction velocity is u. U into area is dy into 1. What is dq? Area is dx into 1 and velocity is v. Dx into 1. So it is u dy, but velocity v is in negative direction. So we take downward as negative and right side as positive, minus v dx. Okay, so it is nothing but psi 1, negative of psi 1 plus positive of psi 2, or whatever you can write in the mod form. Okay, so you can write in a mod form, that is nothing but mod of psi 1 minus psi 2. That is your discharge. Okay, all right. So this is yours. Let me write both sides. If you integrate both sides from psi 1 to psi 2, your q will come out to be mod of psi 1 minus psi 2. Mod of psi 1 minus psi 2. I hope this proof is clear. Okay, proof is all right. Let's take a short break and then I'll jump back. Okay, let's start back. This is just a moment. Okay, we have proved. Hence proved. Let's write that. Hence proved. Okay, now what is the relation between this equipotential lines and constant stream function lines? Okay, the lines which are same potential, the perpendicular one in the flow net. Relationship between equipotential line and constant stream function line. Constant stream function, that is your streamline. Okay, so from mathematics we know that the product of the two slopes is nothing but negative. Since we know that first slope with cross product of second slope is given negative of -1. Okay, so our flow net is defined like this. Suppose these are your streamline psi1, psi2, psi3, and your flow lines are like this. Potential lines are equipotential lines are like this: phi1, phi2, phi3, psi1, psi2, psi3, and both are perpendicular. Okay, perpendicular. So what is the equation of streamline? Streamline. What is the equation? Anyone is asking any doubts? Streamline is defined by dx by u is equal to dy by v. Okay, so from here, what is dy by dx? Dy by dx is v by u, v by u, and that is nothing but your first slope, that is m1 from the streamline. And from the product, because both are perpendicular to each other, phi lines and psi lines are perpendicular, so m1 cross m2 is -1. This implies what is m1? V by u into m2 is -1. So m2 is minus u by. So this is your relation. Okay. So v by u is your first slope for stream function lines, and u minus of u by v is your second slope. Okay. Second slope. Okay. So slope of streamline is v by u. Dy by dx is v by u. So what is? So if I say, I'll draw an axis here. First of all, let me mark them. Okay, we mark them. So let me draw an axis like this. This is y-axis. This is x-axis. This is my streamline. We know that the potential stream function is same psi and psi. Okay, so d psi is 0. And if I draw y and x over it, projections. So this is dy, this is ex. Okay, my d psi is 0. So what I can say, slope of streamline is dy by dx. Okay, from the slope. And what is y? Dy by dx is nothing but v by u from stream function, stream relation m1, v by u. And what is v? It is dou psi by dou x by what is u? Minus dou psi by dou y. Okay. This is your slope in another sense. Also, remember that for irrotational flow, psi and phi both are defined, whereas for rotational flow, psi is defined, phi is not defined. What is a flow net? Okay. So let me write for irrotational flow. For irrotational flow, psi and phi are defined. Now let us write the definition of flow net as well. What is flow net? Although we understood. So it is nothing but a graphical representation of Laplace equations of psi and phi. Of stream function and potential function. Okay. Flow net is defined for both. When otherwise flow is rotational, then only stream functions will be there. Flow net is drawn for irrotational flow, and it can't be drawn for flow net is drawn for irrotational flow, and it can't be drawn for viscous flows, because if viscosity comes, we have understood that there will be torque, presence of torque in that from the past tutorial, and because of the presence of torque, there will be rotationality. So viscous flow, first is viscous flow. Second is within the boundary layer. So within the boundary layer, again, viscous action happens up. That is why there is a gradient of velocity present, and because of that shear stress present, torque is present. Okay. Within, so rotationality will come into play. So you can't define a flow net because phi is not defined for a rotational flow. Within boundary layer, next, sudden expansion and contraction. Again, when you do a sudden expansion contraction, then also there is an issue. So within boundary layer, like suppose I have a plate like this, and the flow goes like this. So flow net, here the flow will be rotational. You can't define flow net, but for irrotational flow outside the boundary layer, flow net can be defined. This is nothing but your boundary layer. Boundary layer BL. Okay, if your flow is happening like this with U infinity, because gradient is zero outside the boundary layer, but not inside. Sudden expansion and contraction. Sudden expansion and contraction. Sudden expansion and contraction. So suppose my just a perpendicular scenario here. So my flow was flowing like this, but suddenly it expanded. Okay, it expanded. So no flat will be here. Okay. If you have pipe ends, then also it is not defined. Okay. If the pipe end is also there, then also it is not. Fourth, we have the pipe ends. So because of the bends and all, that is why it doesn't define. But when the flow has become steady, then you can define a flow net. Suppose I have a pipe like this. So if my flow has been fully developed, suppose we'll understand this fully developed and everything. So again, I can define my flow net here. Okay. there can be a kind of flow net which has decreasing area as well, like this. So, okay. So there can also be a flow net like this as well. So flow velocity of flow is inversely proportional to the area. Hello, am I audible? Am I audible? Hello? Yeah. So I was saying for inversely proportional to area also. So you can define the flow net. Okay. So here velocity of flow is inversely proportional to the area. Okay. As the area decreases, velocity increases. You can again define your flow. All right. Now coming to the Cauchy-Riemann equations. I'll just briefly introduce what are these Cauchy-Riemann equations. Cauchy or Cauchy-Riemann's equation, Cauchy-Riemann's equation. And this is valid. One thing is that only and only for irrotational flow and 2D incompressible flows. This is valid only for irrotational 2D incompressible flow. Okay. And this equation used to find the conjugates of each other. Okay. Conjugates of each other. This equation used to find the conjugate function. Conjugate function. Okay. So we know that your velocity u is nothing but in Cartesian coordinate, it is written as minus dou phi by dou x in respect to potential function. U is minus dou phi by dou x. V is minus dou phi by dou y. And U is minus dou psi by dou y with respect to stream function. And V is dou psi by dou x. Okay. So, oh, sorry, I think my battery of iPad is low. Let me connect it to the charger. I think works fine. So both are u velocities. So if I compare both of them, so this gives me my dou phi by dou x is equal to minus dou psi by dou y. So I can write like this as well. Dou phi by dou x is equal to dou psi by dou y. Okay. So it's giving me the conjugate of each other. Whereas if I equate these two, so that means because both are velocity v's, so minus dou phi by dou y is nothing but dou psi by dou x. Dou psi by dou x. So if you have a potential function, you can directly get the stream function or a vice versa conjugate of each other. This is in Cartesian coordinates. Suppose I go through the polar coordinates. So let me do for a polar coordinates an analogy like that. In polar coordinates, so let us draw something like this. A fluid element is like this. Okay, and it is pointing to So velocity along the radial direction is this VR, whereas along the theta direction it is p theta. Okay, this is angle d theta. Okay, so this arc length will be r d theta, right? And this is your radial direction change VR. Okay, right? So we assume that this is v theta direction, so it is positive, and this is VR direction, this is positive. This is our sign convention which we are following. So velocity in the radial direction will be written as minus dou VR by dou R, and velocity v theta will be written as, sorry, not dou VR, dou phi by dou R, okay, in terms of potential function, and dou phi by R d theta minus dou phi by r d theta. That is your p theta. Whereas in terms of stream function, if you write, let me write them here itself. In terms of stream function, if I write, my VR is minus dou psi by r d theta, and v theta is dou psi by dou r. And again, if I compare them, because both are equal, that is velocity only. So it is dou phi by dou r is equal to dou psi by r d theta, dou theta, and it is dou phi by minus dou phi by r dou theta is equal to dou psi by dou r. Okay, these are your Riemann equations. That is to find the conjugate. If theta is known, the other conjugate phi can be known, both in Cartesian and polar coordinates. Okay, these are your equations. Okay, and what is the equation for rotationality in polar coordinates? I'll just give a brief of it. We define for the Cartesian coordinates, that is omega of the z direction is dou v by dou x minus dou u by dou y. But in terms of z, so let me write a short note here. Short note. I'm trying to say the rotation equation for polar coordinate system is nothing but omega of z is half of dou by r v theta by r dou r minus dou of vr by r d theta. So how we get that? If I say my general omega is this for any direction, er by r is the radial direction, e theta, and these are the unit vectors, ez by z. Okay, sorry, ez by r again. Okay, so this row is dou by dou r, this row is dou by dou theta, this row is dou by dou z, this is vr, this is r v theta, this is vz. If you remember this, you can get the z component, that is dou of r v theta rdr minus dou vr by r d theta as a total. Okay, so just remember this. You can see the proofs of each and every one of it from the textbooks. I'm not interested in going through long derivations right now. So again, we come back to the vortex motion. So I'll just take a short break because we have for a minute or two. Let's then start the vortex motion. Okay, so we come back to the vortex motion. So we have understood that what is a vortex motion in previous tutorial. That is a fluid moving in a circular motion. It's called a vortex motion. So there can be a possibility of rotational vortex motion as well as irrotational vortex motion. Uh, that also we have discussed that when irrotationality comes, that means during the circular motion, the individual fluid particle is not moving across its own axis, but it is moving, the whole fluid is moving in the circular motion. But in a rotational vortex, it is also moving along its axis, when the fluid particle is spinning along its axis as well as in the circular motion. Then they can have tangential as well as radial components of the velocities. Now we categorize our vortex motion in two different forms. That is, one is force vortex and one is free vortex. So what do we mean by a force vortex? That means we provide some external torque to the system so that the rotationality happens. Whereas the free or natural vortex is that without giving any external torque to the system, the flow is moving in a circular motion. So if my external torque is present, that means force vortex. That means I'm giving it is a rotational. It will be a rotational. Force vortex is rotational, whereas free vortex is irrotational. We don't give any extra external torque out of it. So let us write vortex motion. I hope I'm audible. Is there any doubts? No doubts? Okay. So someone is asking where we will get the notes. Yeah. So again, as I said in the start, that these PDF notes will be available through my Google Drive link. So the sheet is given by you, mailed to you by Nptel team, where you get all the video lecture links as well as the Google Drive link. Those who have registered for the course. Whereas those who are seeing directly from my channel, YouTube channel, that is Nptel with Varnit. So all the recordings are there in my playlist of the course fluid mechanics. Similarly, for the past semester courses I have done, all the playlists are available. Corresponding to each video of that playlist of the course, you will find the video description. In each video description, there is a Google Drive link for all these PDF notes. Okay, I update them immediately after tutorial. Okay, so let's start with the force vortex. Okay, force vortex. So that means external torque is non-zero. You are providing some external torque. Okay, so that means flow is rotational. And if flow is rotational, that means only stream function is present. Now you can like make a series of understanding that when the flow is rotational, that means external torque is there. That means stream function is defined. That means it is a force vortex flow. Okay, so vortex motion I'm taking. My flow is circular in nature. I'll again draw the diagram. Yeah, my flow is circular, moving in a circular motion. So that means I have a velocity v tangential, non-zero, but I am assuming that my radial velocity is zero here. Why? I don't want the flow to be spiral. I just want the flow to be only circularly moving, not spirally also moving, because of the presence of VR. Okay, only V theta is there. So if external torque is non-zero, rotational flow is there. So that means my V theta is how much? The tangential velocity is R into omega, whatever the angular velocity of the system is. So if I go to the relation, what is my omega of Z? I just wrote the above this omega of Z from here. That is half of R V theta, the rotational value, half of dou of R V theta. Let me also tabulate it. So I'll choose this dou of R V theta by R dr, R dou R minus dou VR by R d theta. So we assume that radial velocity is zero. We don't want spiral motion, so this is automatically zero. Whereas what is V theta is r omega. So this is r square omega by r dou r. Okay, r dou r. So if you try to differentiate, omega is constant. With the constant angular velocity the system moves. Omega, let's take it out. Dou r by r, and r was also here. So dou r square, that is 2r by just 2r. Yeah, 2r. So this 2r cancels out. You are just left with omega. So omega of z is nothing but your omega. Okay, omega of z is omega. And point to again note here is that if my rate is something like this, okay, that means my v theta is r omega. So with the radius, my velocity is proportionally increasing in the radial direction. So I go in the radial direction, velocity is increasing. So that is v theta is r omega, that is v theta is proportional to radius. V theta is proportional to radius. All right. Coming to the free vortex. Coming to the free vortex scenario. Let me write. Free vortex. That means my external torque is 0. External torque is 0. That means there is no v theta as no, there is no VR I am taking. V theta will be there, and we need to find out what will be the expression of V theta. We are not giving externally. So we need to find out what will be the V theta then of the system. So that means it's an irrotational flow, first of all. So that means phi and psi will be there for irrotational flow. If I'm saying external torque is 0, so torque is nothing but force into perpendicular distance 0. Am I right? Force into perpendicular distance. And what is force? Force is nothing but change of momentum. From mechanics, we can write that change of momentum v into r is equal to 0. So v is only the radial, since we are assuming since v r is 0, therefore v theta is non-zero, which we need to calculate. So this is dou t by dt of mv theta r. If I take this inside, equal to 0. mv theta r equal to 0. So this is your torque. So if some differentiated is 0, that means that value is constant. So that means mv theta r is equal to constant. If I take m is also constant, so v theta is nothing but c by r. So that means my v theta is inversely proportional to r. Yeah, v theta is inversely proportional to r in our scenario, right? So earlier my v theta was directly proportional to r, but here my v theta is inversely proportional to r. Okay, so this is something like a v theta into r is constant. It's a hyperbolic scenario, hyperbolic. So I can say if my plate is like this, where it is flowing, and this is my axis of the flow, and the flow is irrotational. Yeah. So v theta is inversely proportional to r. So my profile will be something like this. So when r approaches to 0, velocity profile approaches to infinite. Okay. Okay. So that is v theta is inversely proportional to r. So I can write together a diagram for it. That is for my plate scenario. This is my plate. I can make this till here. So it is following. That is v theta is directly proportional to r. oh sorry, V theta is directly proportional to R. So this scenario is of free vortex. Forced vortex. This scenario is still forced vortex, whereas for free vortex, it is going like this. So I can say V theta is inversely proportional to R. This scenario is still forced vortex. Oh, this is free vortex. This is forced vortex correspondingly. Okay. So right hand side is free vortex, left hand side is forced vortex. And at R, when R is approaching to 0, this implies V of theta approaches to infinite. Okay. So it's a maximum value. It is not a fixed maximum value. Yeah. So omega of Z, also one can write that omega of Z is nothing but half of rho of R V theta by R dou R minus dou of VR by R d theta. Yeah. So this is 0 because we are assuming that the flow is not spiral. And we say that flow is irrotational. So that means 1 by 2 of dou of 1 by 2 of, I'm showing the another way to do that. First I did through the momentum, force torque is equal to 0, but now is nothing but 0 for irrotational T. Okay, for irrotational T. Irrotational free vortex. That means my V theta is some value. So this value comes out to be 0. So R V theta is a constant value because differentiation of some constant is 0. So this implies V of theta is inversely proportional to R. Once again, a different approach to do this. So since V theta is C by R, so if I go to free vortex condition, I'm here only in free vortex. So if I can do like, I can just write like C theta is equal to C by R, and I can bifurcate it for two functions because both psi and phi will be defined. So how you will get psi and phi for psi and phi. So you know that phi of theta is nothing but dou psi by dou R, dou psi by dou R, and dou psi by dou R, V theta is nothing but C by R, constant by R, dou psi by dou R. Just do the integration, dou R or dou psi is equal to 1 by R dou R. Just write like this, C by dou R by R integrated. So psi will comes out to be C ln R plus some constant C1 or C2. This is C1. Okay, this is your expression. Whereas for phi, we know that V of theta can be written as minus dou phi by R dou theta. And again, V of theta is C by R minus dou phi by R dou theta. Okay, so again do the integration. This R and R cancels out. So dou phi is nothing but minus C dou theta integrated. So this is phi is equal to minus C theta plus C2. This is your other expression of phi. Okay. So if you have a source and sink condition, this is for the free vortex condition you have to prove. And for source and sink, it is just opposite. For source and sink, you need not to go into the proof, but just remember that if a condition is like source and sink, then their psi is minus c theta plus c2, and phi is nothing but c ln r plus c. Okay, c ln r plus opposite of the above. All right, any doubts? No doubts? Okay. So I think we are done with the fluid kinematics completely. And now we'll proceed to the fluid dynamics. Fluid dynamics. But for the meanwhile, we'll take a short break and then we'll start with the fluid dynamics. Okay, so now let's come to fluid dynamics. Fluid dynamics. So currently we are doing the fluid kinematic section, but now we have started with the fluid dynamics. So in fluid dynamics, we deal with the study of motion of the fluid with reference to of the forces and movements. Earlier in kinematics, we were only dealing with the study of the motion of the fluid, like what is the acceleration, what is the velocity, okay, what are the positions. But here we are dealing with study of motion of fluid with respect to or with reference to the forces and whatever the movement is applied. Okay, so in the fluid flow, there are different types of forces which are present. One is like pressure forces there, other is viscous forces are there, surface tension forces are there, gravitational forces are there, elastic forces are there, turbulent forces which involve eddy stresses, we have seen that, and other different types of forces are available, okay, in the literature as well, okay, on which the studies, the research goes on basically. So these forces are very important for the, like if you want to that's why in the mathematical for the simulations or developing some analytical framework for getting the fluid flow behavior. Okay, so that's what the research take part in when I'm doing my PhD here. So I take at IIT Delhi. So different forces involvement, modeling of different kind of forces, how you are disguising your equation for the different forces, the pressure, surface tension force, you solve. And that discretization is then dealt with in the computational fluid dynamics part. So this course has also I've taught it last year, okay, and it will be available on my YouTube channel. You can, if you haven't, if you want to do any advanced topic learning, so you can check out that course. Okay, so what is fluid dynamics? It's basically study of motion of fluid with reference of forces and moments, is known as fluid dynamics. Okay, in a fluid flow, there are different types of forces like pressure force, second viscous force, third surface tension force, fourth gravitational force, okay, fifth elastic force. I hope I'm audible, right? Just check it. Next is turbulent force, which involve eddy stresses and other different types, etc. Okay, so there is a fluid element like this, a random fluid element. Okay, so multiple forces act. That is, one is pressure is acting, which we have seen before in other set parts. Then there is some viscous force which acts, which resists the motion. If V, and there is a gravity which acts. If C. Okay, So as per the Newton equation, what is the Newton's second law? Net force is mass into acceleration. Okay, from the Newton's law, states that summation of net forces is nothing but mass into acceleration. What are different forces? Suppose pressure force, viscous force, gravity force is nothing but your inertial force. Mass into acceleration is nothing but your inertial force. So this is Navier-Stokes equation, where all these forces incorporate. Okay, Navier-Stokes, very important equation. Navier-Stokes. Sorry. The heart of each every fluid flow problem. So this is stands for pressure, viscous, gravity. Okay. When we say that my viscous force is absent in the flow, if Fv is 0, then it is a non-viscous flow. Okay. And then I am just left with inertial forces sum of pressure plus gravity. And this is nothing but your Euler's equation. Okay, Euler's equation. So Euler's equation was derived in, I guess, 1755, and Navier-Stokes was came up in 1840. Okay, and if you do the integral form of this Euler's equation, you will get nothing but your Bernoulli equation. Integral form is nothing but your gives you energy equation, which is nothing but your defined by Bernoulli's equation, and it came around near 1738. Okay, so from Euler equation you can also get Bernoulli's equation, but Bernoulli equation was separately derived in 1738, way past before than the Euler's equation. Okay, but if you do the integral form of the Euler's equation, you will get this energy equation, that is nothing but Bernoulli's equation. So we'll come across with few non-dimensional numbers because these are forces present here. So we will non-dimensionalize these forces in terms of non-dimensional numbers. So my first number, very important number in the fluid, is nothing but the Reynolds number. And it is defined by the symbol small capital R. Re is nothing but the ratio of inertial to that of viscous forces. Inertial to that of viscous forces. So I'll write here inertia. Okay, inertial to that of viscous forces. So what is inertial force? That is mass into acceleration. What is viscous force? Shear stress into area. Okay, shear stress into area. What is mass? What is mass? Mass is nothing but density into volume into acceleration is speed over time. Okay, what is shear stress? Mu v by h, if we assume the linear profile assumption. Mu v by h into area is nothing but your L square. L square. Okay, so volume is L. L is nothing but your characteristic length. Characteristic length. Let us define by LC. So volume is LC cube. Okay, density is density. Volume is LC cube into what is speed? V only. What is time? Time is time only. So speed and speed cancel out basically. Okay, so why to write 2 times? I hope I'm right. Or you can say LC by T. So volume is LC cube into LC by T. So if I assume that L into D into H. LC is my characteristic length, volume is LC cube, area is LC square, is 1 by T, mu, H is again LC into LC square. Okay. So what do I get? Tell me. Shear stress is nothing but mu V into H, shear force, into area, that is LC square. Mu V into LC square, V and V cancel out by LC, mu V LC. So let me write here V itself. So V is nothing but LC by T V is LC by T. Okay. And this is V again. This is again LC. Okay. Am I right or wrong? Density is rho only. Mass is density into volume. Density is rho. Volume is LC square into LC by T into V. Okay. And shear force is shear stress into area. Shear stress is mu V by H into area, mu V LC square by LC. So I keep it this V as V only, and here as well V as V only, V by T. Okay, am I right? Or is there an issue? So this is, in denominator it is mu V LC, and what will be in the numerator? So can I write time as distance over speed again? Can I write that? Am I right? Or can I write or I can write, right? Okay. So it will be rho V square LC square eventually. Okay, if I write time as distance to speed, LC. Okay, LC by PC. Okay, I think students are confused. I'll write this. So this is LC cube. V as V only, time as LC by V. Okay, so can I write like this now? The rho LC cube by LC, that is LC square V square by mu V LC, right? So LC cancel out, V cancel out, rho V LC by, can I write like this? So my Reynolds number is nothing but rho V LC by, this is a Reynolds. Clear? I think it's pretty much easy. Rho V characteristic length by mu. LC is nothing but your characteristic length. Okay. So characteristic length again can be defined for you can say external flow and internal flow. If my flow is right for external flow and one is internal flow. How to get this characteristic length LC? So if my flow is external, that means suppose I have a plate like this, and my fluid is flowing over this, and it is coming with the velocity u infinity. Okay, so this is my displacement x. Okay, along this. So what is the critical Reynolds number for a fluid over a flat plate? So Re critical is nothing but 5 into 10 to the power of 5. This is your critical Reynolds number, and your characteristic length will be nothing but whatever over the flow plate the flow is happening. So it will be x. If the plate length is x, then it will be x. So Reynolds number will be rho u infinity, with which flow is coming, into x by viscosity, dynamic viscosity. So this is free stream velocity. Okay, free stream velocity. Okay. Whereas if my flow is internal, so suppose my pipe, I have a pipe in which flow is happening. Okay, and the diameter of the pipe is nothing but d. This is your pipe, and flow is happening. So here the characteristic length will be nothing but your diameter out of which the flow is happening. Okay, so here Reynolds number will be rho v, whatever the flow velocity is, with the velocity v into diameter by viscosity. Okay, diameter by viscosity. Okay. But suppose the duct shape is not like us, or a pipe shape is not like this. There we have a duct. Okay, so I have a scenario like this. I have a duct through which, and it's a internal flow through the duct. Okay, so there is a velocity v. So here in such scenario, my characteristic length dh, that is, will be 4 into cross section, 4 into area of cross section to perimeter. Okay, so what is the area? 4 into, suppose this is A, this is B, 4AB to 2 of A plus B. Okay, for such kind of cross section, 4AB and 2 of A plus B. So this will be 2AB by A plus B. Similarly, if you do for circular here also, area is pi by 4 d square by perimeter is pi d. Again, it will come out to be diameter of this. Okay, so in such scenario, so let me first write the Reynolds number for a pipe. So I'll take it down. So in this Reynolds number for a pipe flow, circular pipe, Reynolds number, if it is less than equal to 2000, it is said that the flow is laminar. If Reynolds number is greater than 2000, that means it is turbulent. Okay, for circular pipe. Circular pipe. Okay, whereas for a duct, this will be a different story, and Reynolds number as I've told, but in a duct, the Reynolds number will be rho v dh by, and your dh will be coming from here. Okay, so again, if Reynolds number is less than 2300, laminar, greater than 2300, it is turbulent. Okay, any doubt? And there can be a scenario of an open channel flow in an internal flow. So that is what we want to deal with. But open channel flow is like this, but flow is still here. Okay, some channel is open to the here. Okay, all right, but we want to deal with it. Next non-dimensional number is Froude number. Froude number. The Froude number is nothing but f of r is inertial to that of gravity under it. So what is inertial? Just now we got rho v square LC square, and gravity is mass into acceleration. Mass is density into volume, rho into L cube, and acceleration is meter per second square. So it is L. Let us keep it as gravity. So rho into LC cube into G. So it will come out to be V by the root of LC by, that is your root number. Okay. Similarly, there is one another non-dimensional number, that is your Mach number. So it is nothing but Mach number is nothing but ratio of under root of inertial to that of elastic force is present. Okay, elastic force. So this is your elastic. Okay. And elastic force can be written as, in the terms of fluid, that is K into A. K into A. So area is LC square, and A and inertial is rho V square LC square, and K into LC square, right? So it will comes out to be rho V square by K under root. So it is V by, take out the square root from inside, V by K by V by the root rho. So that is V by under root of K by rho, property of that fluid. So that is V by, that is speed of sound in that medium. This is nothing but your speed of sound. All right. So this is your one. I hope this is clear. So I guess let's end till here, because we will start with the next topic of Bernoulli equation. It will take time. So we'll start with that in the next tutorial. And let me again tell that all my lecture videos are available on my YouTube channel. What is the name of the YouTube channel? The name is NPTEL with Varnit. This is the name of my YouTube channel. All the lecture videos you will find in this channel for every course. Currently, we are running with the fluid mechanics course. In the playlist, if you go, you will find this. Those who have registered for the course, they can easily get the sheet from the Nptel team. We have the names of all the lecture videos from me. My name is Varnit Kapoor. All against my name, you will see the lecture videos as well as a Google Drive link for the PDF of these notes. And those who are watching directly from my YouTube for the initial time, not registered in the course, they can see the video description. And each video description, there is a link to the Google. You can check out. So if there are no doubts, we can end the session. So I'll see you next Tuesday. Same. Take care.